Hello friends, I am Pradeep. Today's topic is very interesting as well as this problem is very common and it is very simple, and we are going to think on, and we are going to see this problem, and this is a very general problem, and it is a very common uh, problem which you have seen in your daily life, and really we will enjoy, and it's my request that please be patient, and keep your eye just focus on. We will see very interesting things. I have a doubt in my mind. What is doubt? Doubt is that, let there are two materials, any two materials. Material, let any material is steel, another material is different type of steels, or different type of ferrous or non-ferrous, any type of material. I'm telling you, which has some modulus of elasticity. Another material will have some other modulus of elasticity. Means both materials will have its own material properties: stress strain curve, modulus of elasticity, yield strength, ultimate strength. It means completely they are different materials. Okay, so my doubt is that, and of course I would I have seen this doubt in a lot of the people, and they say something some people say it would be like this, other people will say it would be like this. It is the thing. And how do you think? Just just you see, when what is the fact, we will also see in the last. Now we'll again see what is the doubt. I'm asking, I'm asking you, or you can say that the doubt is that, let these are two materials, okay, and they are having same geometry. Same geometry means they are having same length, width, and thickness, and also they were going to be applied under the same loading conditions, same boundary conditions. Let one is a fixed at one end, another, I am taking with a simple problem, because you know that there is a concept behind every big thing is very simple. So we are going to explore these things with a very simple problem, so that we can understand in a big scale. Okay, so yeah, my problem was that, let there are two materials, and also they are identical with the geometrical configurations, and as well as they are identical with the loading configurations. Okay, so if you are applying, you know that if your geometrical and loading configuration are same, so the doubt is, or you can say that doubt or questions, anything you can understand, what would be the stress developed or induced in both the bodies? What would be the stress? Either they would be same or different, or what would be? You know the question. I think you got it. Question is, there are two materials, and both materials are completely different. Completely different. One is having very high modulus of elasticity. One may have very low modulus of elasticity. Okay, and so they are completely different materials. I'm sorry. I'm so I'm sorry. So so these are these are the two materials, and which are going under the same loading conditions. So I'm interested that the stress induced in both the bodies, which is made up of different materials, either stress induced is the same or not. We know that stress is actually is the is the stress is proportionate with the strain. Okay, and if one body will have if one body will have higher modulus of elasticity, so other body, so that body, uh, let us, I am going to with the, these are the this is the problems, actually this is the problems what I have discussed you with both the there are two materials. One is having high modulus of elasticity, means one is one material, and there is another material, and both are going to be applied with the same loading conditions. So the stress is going to be same or not, that is the questions. Now what is the doubt behind the many people's first doubt is that people said, if the material will have high modulus of elasticity, means high modulus of elasticity means it has a high that means it's more stiffer material. Okay, because it will high, it will have a high, it means in stress strain curve that will have a high slope between the stress and curve is large. So this is a more stiff material, because modulus of elasticity represent the stiffness of material in the second phase, you know that. So people said, if it is a very high stiff material, so if it is a high stiff, so strain will be lower. You know that if any material would be very more stiffer, then you cannot deform it. Okay, because uh, the deformation in that material will be less in comparison to that material which is having less modulus of elasticity, which is having less modulus of, means, so the for the same magnitude of the force, the strain in the second body which is having the less modulus of elasticity will have the less strain value. So people said, if it is having less strain, and another side less strain for the lower stiffer less stiffer material, another side the material which is it is very stiff. Okay, and it is having modulus of elasticity is very high. So the strain value in case of the high strain, in case of high stiffer material, it will be lower, and in case of that lower stiffer material, we will have a higher strain value. So it is obvious that would be, there is no doubt in this one. Yeah, it's fine. Then they argue that, if the strain is less in the less in the high stiffness material, okay, the material which is having very high, very very it's very stiff, you can say that, na, it's high, you can say it is very hard material, very stiff material. So they said that if this strain is less, because stress is directly proportional to strain, then stress will be lower in that material in comparison to the less stiff material. This is the question mark domain. Is it is 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 that actually they were correct or not? Means the material who is having high stiffness value, high modulus of elasticity value, will have less stress, means stress induced will be less. In other case, the material in which the will have uh, that have a property with less modulus of elasticity value, will the stress induced in that material will be high, because the strain will be high. Strain will be high in the less stiff material. So if strain will be high, because stress is proportional to strain, so stress will be high. Now come to the second group of people said that, they said, yeah, it is stiffer material. Okay, it is stiffer, I agree. So this will take more force. This will take more force to deform it. So this will have a more stress value. It is just, there is no basis behind it. They tell like this. I'm telling you, there is no basis. They just said it is a more stiffer material, and it will take a more load to deform it, and so this will have a more stress value. Another side, they said, this is a less stiffer material, it will take a less load to deform it, so less force, less load to deform it. So the resistance, so stress developed in the body will same. But I am talking about, if we are applying the same force in both the bodies, what is going to be happen? Okay, so these are the two type of people said about this problem. Now my today's this discussion is about this whole the things that we have discussed, that we have doubts and discussed all these things. What would be the stresses in both type of materials, and the doubts that people having, and we'll clear all these things, what is going to be correct. And also we will see with the finite element software, we'll see theoretical formula, we'll also see the finite element software, and we also see the concept behind this. And you know and you will see the concept and the fear calculations using any softwares that will give the same results. And then then you will understand the complete picture about the stress, about the stresses, the concept of the stresses, simple in case of applications, not the basic stress definition and concept of the stresses, like stress at a point, what will not like this. Just the application of the stresses. I am talking about the application of the stresses. Okay. Here now let us focus on this complete approach. I'm just defending this complete approach. I'm having these two materials. One is having modulus of elasticity value is 2 into 10 to the power 5 MPa is the symbol of the engineering or scientific application. So we can, you know that we are all engineers, so you would be very well. Another material is having E value, that is the modulus of elasticity value is 2 into 10 ki power 20 MPa. So this material is very stiffer as compared to this material. Okay. So this is the material properties. Okay. So this is the less stiff material, and this is very high stiff material. Now come to the geometrical configuration. They are identical. This material block has a length of 100 mm, and it has a width 50 mm, and it has a thickness 1 mm. Similarly, this material have the same geometrical configuration. Now come to the boundary condition. At one end of this material, this block of the material has been fixed, and another end of this material has been spooled by a force of 500 Newton. And similarly, this material has been also fixed by at one end, and okay, another side it has been pulled by the 500 Newton. Now now we'll see what would be the stresses induced in this block of the material, and what is the stress induced in this block of material. And we have seen that these two blocks are made up of different materials. This block is belongs to the steel type of material, and this block is very stiffer than steel, because this having the modulus of elasticity value is very high. It is 10 ki power 20 power, is the power of 10 is 20, and here is the power of 10 is only 5. So you can see here this is very high stiff material, and it is very less stiff material. So we'll see the stress induced in both the blocks either will remain same or not same. If not, then why? Okay. So here we can calculate the change in length in the block 1. I'm just looking at the change in length in block 1, this block, which is having the modulus of elasticity 2 into 10 to the power MPa. Okay. So we know that the formula by the basic mechanics, because we are all mechanical engineers, so we know that this is the change in length equal to PL by A. Okay. So P is P has been given here is the 500 Newton, and the length of this block of the material is 100 mm. Okay, and multiplied by A is the cross sectional area. It is the cross sectional area is actually I have given the 50 mm of width, and the thickness is 1 mm. So 50 by 1 mm is the area of cross sections, and E is the modulus of elasticity, which is given here 2 into 10 to the power MPa. Okay, so we'll just solve it. P is given here. F is actually P. So it is actually 500 Newton. 500 multiplied by length is 100 by 100, but okay, divided by A is the 50. okay, multiplied by 1 and multiplied by 2 into 10 to the power 5, then if you solve it, then we'll get it 0.005 mm. Okay, this is the change in length of this this material block. Okay, so this, okay, and then the strain formula, we know that the strain, engineering strain, is a change in length over the original length. Change in length that we have estimated from this formula, from the very basic formula that you know all very well known, that is formula del L over del L, del over L is L is the length of this body, okay, length body of block of this material, and we, after dividing it, we will get will get this is 0.00005 mm. Okay, if we have estimated the strain value in this block, so we could easily get the stress value in this block by using the Hooke's law. And Hooke's law is that, Hooke's law said that stress would be proportional to strain, and the proportionality constant is actually nothing but is a modulus of elasticity. So modulus of elasticity for this block has been given 2 into 10 to the power 5 MPa. So stress equals to this value 2 into 10 to the power 5 multiplied by this value. So if you multiply it by calculator, then you will get the 10 MPa value will come. Okay, so now if this stress value has come for this material, for this block of the material. Similarly, I let to you and get this and calculate similar this way for this block. Perform the same calculation for this block. I am requesting you, please take your pen and get back to this lecture after getting this, after performing this calculation. And if you are really true with yourself, then you will do it. And if you do it, then you will get the stress value in this block will be 10 MPa. Really, you will get it 10 MPa. Just simple perform this delta L2 and then epsilon 2 and then sigma 2. You will get sigma 2 is equals to 10 MPa. Similarly, I'm calculating this stress value by another formula that you would be all very known. The stress is then nothing but a resistance of the body. So we get this stress value from other we get stress value from other elasticity value, for means I am talking about this value. So we'll get this value 10 MPa. Same. Similarly, next if we'll calculate the stress value from other formula, this formula sigma stress is equals to P by A. P is nothing but a resistance of the material, and A is the area of the cross. This is stress per unit area, sorry, force per unit area, internal resistance per unit area. Okay, so this is the third, this is the second way of doing the calculation of stress. Okay, so in this calculation we have P, okay, and P is nothing but this value 500 Newton, and A is the cross sectional area perpendicular to this direction. So A is there nothing but a 50 multiplied by A. If you divide it really, you will get a 10 MPa value. You will definitely get a 10 MPa value. So what you have seen, that we have seen that stress developed in the body, in the both the bodies, in the body 1 and in the material body 2. This is material body 1, this is the material body 2. Material body is less stiff material. Material 1 is completely, it is steel, and it is not, and this one is not steel. This is very stiff material other than steel. It has a modulus of elasticity is very high. It is not steel. And we have seen that the stress value, the stress induced value induced in the both bodies are same. It is 10 MPa. Okay, and we have also seen this has been estimated by two ways. First one is simply divided by force by A, and second is actually estimated by the modulus of elasticity. And we have seen that the stress developed in both the body is actually independent of elasticity of the material, because in first case we have estimated the stress value using the elasticity of the material in the same elasticity of the material, and similarly this has been also numerically this has been also calculated by elasticity of the material, and we can found that we have found that the stress obtained in the both the cases are same. So, and the similar in the second way we have seen that stress is actually resistance per unit area, and in this formula you have seen that there is nowhere modulus of elasticity. It is just ratio of P resident resistance offered by this material and cross section. There is no any value or any terms of the modulus of elasticity in this equation. However, there are there are terms in the modulus of elasticity, but after this we are getting the same value. So we can so there is things why it is coming like this, and there is a physical significance, but by mathematically we can see that mathematically this equation and this equation are same. It is sigma 1 is equal to E epsilon and sigma is equals to P by A. Mathematically both equations are same. However, there is multiplication of P, but here there is no multiplication of P, but these equations, but both the equations are same, and because we have seen that both equations are giving same stress value. Okay, I think you got it. And so here that we can conclude a term that the stress developed in both the bodies or stress developed in the body, okay, is independent of elasticity of the material. Whatever the elasticity of the material would be, it means whatever the material you have chosen, if the geometrical configuration of both the material would be same, the stress value developed in both the material will remain same. Don't confuse with that this material is very stiff, this is material steel, this is copper. So if you will apply the same load on steel and same load on copper, so there are two communities that have talked about that. The first community will say this is steel more stiffer, so will it have less stress. Another community will say steel, this will have high stress. So don't confuse with this. Both the material will resist the same stress value if the geometrical configuration of both the materials are same. Okay. Now come to the point. Why this is actually mathematically. I have proven that you have seen that, and the thing wrong is there, and you can also take a pen paper and you get the calculation. If any calculation if you would find, please comment me if you find any, and if you have any thoughts, any confusion regarding these things, you can please comment on this channel. I will appreciate your comments, and I will definitely I will try to resolve your confusion and your doubts regarding the concept, regarding the physics of the problem, anything. I will resolve that problems. Now come to the physics of this problem. This is the mathematically I have explained this. Physics says simple. Mechanics says okay, so this body is very stiff. Okay, so if you apply oh, okay, this body is stiff, this body is less stiff. This is steel, this is a copper, and if you apply this, and geometrically are same both the body, and apply the force, same force on both the bodies. So what is going to be happen? We know that. Now come to the very basic things. This is steel. So if you apply force of 500 Newton here, and this is copper, and if you apply 500 Newton here, okay, and I'm assuming both they are both are in this load, the value of this load they are in the linear region. I'm talking about this one. So so what I'm going to tell you is that, so simple calculation said, if this is steel, the change in length would be less as compared to change in length of the copper, because copper is softer material. It is no doubt, it is fine. Now come to the strain, because change in length over length, because length, if original length both the material will have same, then strain will also be higher in case of copper, because the forces are same in copper and steel. Okay, now go to the calculation of the stress. We know that stress is actually the not to keep in mind that this material will have a high strain value, so it will have high stress. Also, you must have remember that this strain value is coming corresponding of that modulus of elasticity. Okay, if I am talking the linear elastic analysis, so the stress value is actually the product of the modulus of elasticity and the strain. So if the strain if the strain will be higher, then modulus of elasticity will be lower, and the multiplication is take one side. It means, and other side take, if the strain is lower, then modulus of elasticity will be higher. Take the multiplication of one side. So you can say that E1 into epsilon is equals to E2 into epsilon, because if E1 is higher, then epsilon will be lower, and even if you lower, then epsilon will be higher. So this is actually the reciprocal of the things, and if they multiply these two things, you will get the same output. It means same stress value. And also, I have told you some minutes before that this formula, this E1 into epsilon 1 and P by A actually is same. I can show you the one derivation and you will appreciate that yeah, it is same. Here the stress is equals to E into epsilon, means E is the modulus of elasticity and epsilon is the strain. Okay, so this is actually Hooke's law, and by expanding this Hooke's law, strain is change in length over the length. Again we are expanding this equation, because we know that change in length is equals to PL by A. P is the force, L is the length of that body, and A is area of cross section, E is the modulus of elasticity. Therefore, if you put this value in this equation, so we will get stress is equals to E into PL by A by L. And on simplifying above equation, similarly simply we will get P by A, because L will be cancelled by this L, and E will be cancelled by this E, and we will get P by A. So stress value would be P by A. So stress obtained by this consecutive equation E into epsilon, and stress obtained by the simple physics, simple talking about the equilibrium equation. What says it's the action and reaction will be same, because action force, let it is a force P, then the resistance developed in the body will remain same. So consecutive equations, which is the relationship is stabilize the relationship between the stress and strain. You know that stress is a quantity which cannot be physically measured in any. Okay, so there are some techniques that can be, but normally it cannot be measured like strain. It cannot be measured, but strain is measured by strain gauge. So corresponding strain, what would be the stress? It is only determined by the consecutive models. Okay, otherwise it cannot be determined stresses. But here stress, there are other terms. Stress is actually, what is that? This is actually resistance offered by the material. So it is just philosophical. What is the resistance of? How do you get the resistance offered by? So resistance is actually what? It is the force. Whatever you are applying the force, the same force is actually the resistance which is offered by this material. Simply, this is actually the formula which is derived by physics, but is simply mechanics, and this is by the experiment, and there are so many things. This is actually the calculation of this stress is actually by the consecutive model, material consecutive model, which determines the relationship between stress and strain, and this is the simply equilibrium equations, okay, simply mechanics, nothing but. And you have seen that both the stress value estimated by the consecutive model and stress value calculated by the simply equilibrium equation, both are same, and it have to be same, otherwise the body will not be remain under equilibrium. Okay, so consecutive model will have to follow this equilibrium equations, will have to follow, you know that. Okay, so if you have convinced myself with this arguments that the material are different, but still they will have the same with the still will have the same stresses, or the stress induced in the both the body will remain same. If you agree with this me, so you can also agree with this for this problem, that there is a one problem, uh, that there is a one plate which is uh, it is not one, it is one plate, but it is made up of two different materials. One is having very high modulus of elasticity like this, and one is low modulus of elasticity. This has a modulus of elasticity 2 into 10 to the power 5, and this has modulus of elasticity is 2 into 10 to the power 20 MPa, and at one side of this material block is fixed, another side is force is it is pulled by 500 Newton. Okay, so so the same, we, if we have understand the above philosophy, above concepts, all the things, so we can simply say that if, although, and also I'm saying that geometrically these one block and one block are similar material, similar geometrical configurations, but materials of this block is different and this block is different, both are materially completely different materials. And if you have understand the physics and concepts of the that we have discussed, then we'll simply say that the stress induced in this block and stress induced in this block will remain same. However, they both were having the different modulus of means modulus of elasticity, or however they were having are actually they are different materials. They are, let you can say that it is some material that is steel, and it is higher material which is stiffer more than, it is more stiffer than steel. So but after this, the stress value induced in both the block will remain same. I However they are having the different material, however they are very different from the material point of view. Okay, if you understand the concept of this one, now I have told now we have understand all the things by the theoretical formula and physics of this thing. Now the same things we are going to understand with the numerical problems, with the numerical calculation procedures. Numerical, we are going to use finite element analysis using Ansys softwares, and we will see we will see above problems that, like the case 1, we have see that there are two blocks, there are two blocks, and having the material point of view they are completely different, and but geometrically are same, and apply force with the same forces, and we'll get the same stress value. But we have seen by this theoretical formula and all these things, but we are going to see and we are going to solve these two problems. We are going to solve these two problems by using the finite element analysis using Ansys softwares. Okay, and then we will see what is going to be happened here. So let us see. So here, let okay friends, so we are going to see using finite element software Ansys. So let us, we are going to put one another material, because one material is also here, but something they have taken modulus of elasticity value something else that we don't have considered in our case. So we are because okay, so it is fine. So they have taken also 2 into 10 to the power 5 MPa, and also in our one case the modulus of elasticity value is 2 into 10 to the power 5. In another case, that is a more stiff material, more stiff material. Okay, so we have named it as a stiff, and we are taking it as a linear isotropic value, that is what would be the modulus of elasticity. Take it as a MPa, and give it the value what we have considered in our theoretical calculations. It is 2 into 10 to the power 20. Okay, so 2 is E into 20 to the power 20 MPa. Okay, and we'll take the same Poisson's ratio value, and here the Poisson's ratio value is 0.3, and we are going to take the either you also, you may have changed this value. I'm changing this value, this Poisson's ratio. let us I am going to change this value is 0.28. okay, so it is not the not it is not the will not create any problem. okay, I think the name has been removed, so take it, it is stiff material. okay, so one is a structural steel, another is a more stiffer material, and we are going to see the stresses induced in both the materials. okay, come to the modeling point of view, and just double click it, and we are going starting design modeler. okay, so we'll model this geometry that I have given here. It is 100 by 50 by 1 mm. okay, and then we'll apply the boundary conditions and force and get back to the results. So this is design modeler of Ansys Workbench. It has been opened here, and just take it look at, and simply make a rectangle. okay, simply make a rectangle here. okay, but one more thing is here, take the units in mm. okay, so you can also do undo. okay, you can have undo and get back to the units in mm, and then have the and this fit to the screen, and take this rectangle toolbar and go to the dimensioning and dimension it for this horizontal, and this is the vertical dimension. Horizontal dimensions in our calculations we have taken 100 mm, and we have taken 50 mm, this vertical dimensions, and this is zoom to fit toolbar, and make the surface of this surfaces from sketch. Select this sketch and apply, and then generate, and we have generated this sketch, and then get back to the FEA modeler tab. This was the design modeler, simply CAD modeling. Next we have jumped to the finite element modeling toolbar, this tab, finite element tab. We'll apply the boundary condition and then force, then get back to the results. okay, so we are very, I think you would be very aggressive, so eagerness you would be having. So what would be using finite element, what is going to tell the software? Yeah, and it is obvious to have these things, and it shows your curiosity, and this will lead to you definitely, because this curiosity actually the birth of the new things. okay, so simply click here and then just have a thickness 1 mm. okay, and simply you can mesh it. Now I am just applying the boundary condition here, and I'm taking this edge, and I'm not going to fix it here, because in my previous lecture, in my previous videos, I'm requesting you just see the concept of the boundary conditions, how to apply the boundary conditions and all these things. It is my request that how to apply a boundary condition and concept of the boundary condition. I'm just taking it for the case of the simply tensile type of testing, simple uniaxial tensile type of the things, and whatever the appropriate boundary condition I'm taking, because if you are having 1/4, then there would be only one color in whole the body. If you take the fix it here, you will not get the same color, so you will apply some and you will get some stress concentration things, all this here. So it means you applied the wrong boundary condition. So I am not going to explain all this, because I am already have given the one video. So please just watch this look at this video, and and understand the concept of the boundary condition in my previous videos, and you will enjoy very much. I'm 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 definitely I'm saying. So in x direction, take it as 0, okay, and take one more displacement boundary condition. Take this point and take this as, and and take it y 0, y 0 is z is also 0, and also because it has modeled with a cell element, because it is a workbench, you cannot see the what type of element which have been used to model such type of problems, because it's very thin, so you may understand this is a thin plane stress type of problem. So plane stress type of problem will not have the such type of 6 degree of freedom, but unfortunately with this workbench will having the in back end, it takes the it is taking the cell element. So you know that cell element have the 6 degree of freedom at each node, so we have to capture the fixed rotations of this body. Otherwise we'll have that, we'll be trouble in getting the convergence and all this, will not have the okay. So apply the force value, at the other edge, and that value is actually will remain same whatever be used in the calculations, and it is 500 Newton. Okay, so let us solve this problem and get the stress equivalent von Mises stress and strain value equivalent von Mises strain, and also see the total deformations. And let us solve this problem for the while for the material that we have considered in this case is actually the that is I'm just showing you, because you have to take it, drag it here, and so I'm not that just wait for a second. This window, this can be away from this way. So actually this is all for the material of steel. It is default material which has been taken by this workbench software. Okay, so just have a patience, that it is solving, that is evaluating the results, and let us see what the material it is using. This is assignment material. The material has been assigned for this body is structural steel, and which is 2 into 10 to the power 5 MPa modulus of elasticity. Check the equivalent stress. The equivalent stress is coming 10 MPa. You have seen that. You can also animate this one. It is simply a uniaxial type of loading, and if the whole body is having at each point, at each place, if this force is this 500 Newton, so stress value in the whole body will remain same. So that is we are getting 10 MPa. From the theoretical calculations we have also looking here, it is 10 MPa. Okay, also from P by A we are also looking 10 MPa, and this is one way, second way, and the third way is a finite element. Also finite element calculation gives you the 10 MPa value. MPa is a unit, here is the MPa unit. Okay, now let us see the strain value. Strain value we are getting 5 into 10 to the power minus 5 mem per mm. You know that is unitless quantity. So here also you can see that is 5 into 1 2 3, it is 4 5 into 10 to the power minus 5 it is a strain value. Okay, so let us see the total deformation. Deformation is maximum deformation, here it is coming 0.005, 0.005. You can also see here the maximum deflection, that is your displacement, you can see 0.005 we are getting from theoretical equations. So stress, strain and deflection or displacement, a change in length, that is we are getting from this simple calculation, simple theoretical calculations, and also we are looking the same results from this from the finite element software Ansys. So one side my objective was not to to compare the theoretical and numerical results, to understand the boundary condition, to understand the modeling, to understand the software thing. Our objective was different, you know, that to that that another you can think on, yeah, it is correct, that's why it was matching, that is one way you can think on. But the main core objective was that if we are changing the material body, okay, if you are changing the changing the material, then the stresses in value induced in this body will remain same or not. And we have seen that from the theoretical concept of point of view, from the mathematical equations, it is same. So we are also looking with the finite element softwares, okay, using finite element methods. What does finite element gives, what does finite element will give you, that is our thing. And that we have seen that if you are taking the material is structural steel, having the modulus of elasticity value is 2 into 10 to the power 5. So we have seen that stress induced in this body for this material, which means for steel, is 10 MPa, and the strain is this value is to 5 into 10 to the power 5, and the total deformation or total change in length is actually coming 0.005, which is exactly same as the theoretical calculations. Okay, now come to the second material. So assign the another material that is stiff. Now you have seen this is the some symbol has been come up, yellow symbol. This says solve it again. Now I'm solving it again for the different materials, which is very stiff, that we have defined that in the engineering data that you have seen already. So this stress and strain value will be corresponding that is stiffer material, that is having the modulus of elasticity value is 2 into 10 to the power 20. And we have seen, now you can see here the stress value is remain same, it is 10 MPa, it is not changing with respect to material. Okay, so either you take copper, either you take steel, anything, if you are doing the linear static analysis, the stress value is not going to change with your changing the modulus of elasticity value. It is not either Poisson's ratio, either modulus of elasticity, it is not going to be changed here at any cost. And this is the third way of doing. The first and second was using mechanics, and third way is the finite element analysis using finite element analysis method by the Ansys software. Okay, and look at the strain value, but strain value will change because strain is the sum is strain is actually dependent on the modulus of elasticity. That's why strain has been changed. A strain value is coming 5 into 10 to the power minus 20. Okay, but stress is remain same. If you will, that I have led to you, that please take your pen and please have some efforts on your brain and on the hand. I'm requesting you do the same calculation, repeat the same calculation for this modulus of elasticity value. Either if you are very strong man, so you can also think on in your brain, and you will get the strain value which is coming here, that is 5 into 10 to the power minus 20, which is as same, which will get from the mechanics formula. Okay, and the total deformation will remain same, that is which is 5 into 10 to the power minus 18. Okay, so strain and total deformation is actually dependent on the modulus of elasticity, but the stress value is actually independent of the modulus of elasticity. And this is my whole objective. This is my whole objective of this presentation, this lecture, this discussion was, it is completed successfully. I am saying you have seen that the stress value obtained by these finite element method, by mechanics, by formula, by physics, it is actually same, and they are saying same. So I request you don't have any confusion in your mind that if the material will change, then stress value will change. It is not like that. Stress value will remain same. It is not going to be changed, but strain and deformation value will going to be changed. Okay, so So I am just letting you that that what how much you are sincere with yourself is going to solve this problem. I have solved both the problem, this and this, and I'm letting you to solve this problem. And if you solve sincerely, if you solve these problems, fix after fixing here and giving the material assignment here 2 into 10 to the power 5, and again assigning the material at this region is 2 into 10 to the power 20 MPa, and apply the force 500 Newton, and keeping this length, it is 100 and 100, take the 200, okay, and take it as take it as a 50, okay, by 1 mm thickness. Then you will get the stress value, stress induced in this body and in this body, that will remain same. It will not, it is not going to change. If any things will happen, please comment on this video, this on this video, and please comment on this on my channel after looking this video. If you like this video, and if you really like this video, if you think on that you have got something new, you have got something new means you know all the things. I know that you are mechanical engineer, you know all the formula, you know all the software things, all you know all the things. But if you really think that you have understood something, you have got something, so please don't forget to subscribe my channel. Okay, thank you very much, because I am very I will always present I will present new, because I'm also I try to present the video in a new way. And new way means that the simple but tricky, the thing looking it is very simple, but actually if you go inside that one, it is very tricky. Simple but conceptual. And okay, so thank you very much giving and having patience. And I request you to please subscribe to update with my new video. And I hope this video would be would fulfill to have your satisfaction level. And the next video will be parallel to that one, and will be simple but very tricky and conceptually, and that the things is like this. Okay, thank you very much. Thank you very much.